So the problem that we looked at in the previous video was given a list of n numbers 0, 1, 2, so on and so forth, n minus 2 and n minus 1, right? This is a list of size n, and this is a list L, and given a query point, let's say 31, we wanted to find if the problem was is Q present in L or not, right? And for this we saw a very simple algorithm which is order of n. And what did we do there? We just checked each of these elements. We just checked whether the 0th element equals to Q or the first element equals to Q, so on and so forth. So roughly we did about n comparisons, and it took us about order of n time, right? So it took us order of n time. What about space? Did we use any additional space? No. So it took us order of n time, and apart from the space given for this program, given for this data, because without having the list itself we can't do anything, right? So apart from the input, here my input for this algorithm was the list itself and the query point. Apart from these two, we didn't use much of space, right? So I would say that I used order of 1 space there. Now the question is, of course, lower the time complexity, the better it is, right? So lower time complexity, the better it is. Similarly, lower space complexity, the better it is, right? Now the big question here is, for the algorithm that we wrote, we had order of n time, right? And order of 1 space, right? For the sequential search, it's called a sequential search because we searched if the element is present sequentially. Now the big question is, can I somehow reduce this? And remember, oftentimes there is a trade-off between time and space. Okay, so binary search is a brilliant technique which says that I can reduce this time from n to log n. And log of n is always less than equal to n. So let's take an example, right? So let's assume log base 2. Okay, let's just take log base 2 for simplicity. Now if you have n equals to 2, what is log n base 2? It is 1 because 2 power 1 equals to 2. If n equals to 4, what is log n base 2? What is 2 power what is 4? 2 power 2 is 4, right? Right. Similarly, if n equals to 8, what is log n base 2? 2 power 3 equals to 8, so it will be 3. If n equals to 16, what is log n base 2? 2 power 4 is 16. So in each cases you'll notice that n is, so if n equals to 1, what is log n base 2? 0. Right? So log n is always less than n. A simple example here that I'm showing you, right? So imagine, so since log n is less than n, if I can somehow write another solution or algorithm, if I can somehow get from order of n time to order of log n, that is brilliant. Because imagine if my n equals to 1024 elements, right? Suppose if I have 1024 elements, using my sequential search, it would take me order of n time, roughly n comparisons, right? 1024 comparisons. But understand what is log n. If log n base 2, 2 power 10 is 1024, right? Is 10. If I can get away with 10 comparisons, right? This is the power of it, right? So order of n basically means I'm doing 1024 comparisons, roughly, or operations. But if I can get away with log n, which is 10, there's a huge difference between 1000 comparisons and 10 comparisons, right? If I can somehow get away with just about 10 comparisons, roughly about 10 comparisons, then my algorithm is obviously much more efficient, right? Log n is much less than n if you think about it. Okay, and you can look at these numbers. When I have n equals to 16, my log n is only 4. When I have n equals to 1024, my log n is just 10. Right? So is there some way for us to go from order of n time to order of log n time? There is an algorithm called binary search. Those of you who have studied computer science would learn about this in your in data structures and algorithms course. Okay, let's those of you who do not know, don't worry, we'll just learn it right now. The idea of binary search is very elegant. Okay, so the first thing that we need for binary search is this. You need the list to be sorted. List needs to be sorted. Otherwise, binary search does not work. List needs to be sorted. Okay, there are sorting algorithms like bubble sort. Those of you who have studied computer science would quickly know this, but I'll not cover that right here. But imagine if my list is sorted. How do I search for an element? Okay, let's take a list here. This is 0. Let's take an example so that we understand what's happening. 3, 4, 5, 6, 7, 8, 9. Let's assume I have 10 elements here, right? Let me also put in the numbers here so that it's easy. Let's say 23. It has to be always ascending, right? Sorted array. 28, 32, 37, 42, 48, 49, 56, and 59. Okay, this is my list L, but it is sorted, remember, right? It is sorted increasing order like this. Every number is greater than or equal to the previous number, right? It's a sorted list. Now imagine my query point here is, let's say my query point is 25. Now I want to find where 25 is. Okay, the way I'll do it is this. Okay, it's called binary search. Okay, so the way I'll do it is this. First, let's take, so what is my initial array? My initial array has, so I'll keep a variable called L at 0. Okay, left, and I'll keep my variable here called right. Okay, when I start, I keep my L to 0, I keep my R to N. So my 9 equals to N, right? N minus 1 actually, because I have N elements here, right? Now what I'll do here is, I'll try to find the middle element of this array, right? How do I find the minimum middle element? My middle element can be written as left plus right by 2, right? I can do a floor operation here. So what I get, 0 plus 9 by 2, right? Which is 9 by 2, right? I can do a floor or a seal, whatever I want. Because this number is not exactly an integer, I'll round it up. This is 4.5, right? Let me round it up to 5. I'm rounding it up. I'm rounding the number. Okay, I'm just rounding the number here. So I get a value of 5. Now I go directly and check what is the value of L5. L5 value is 42, right? First, what have I done? I've computed the middle element. My middle element is nothing but you round L plus R by 2. And my middle element was 5. Now what I've done is, I'll directly go to the 5th location. I'll directly go to the index 5 and I'll check what is this value. Now, is 25 less than 42 or greater than 42? It's less than 42. And since I know that this array is sorted, right? I know that this array is sorted in increasing order. My 25 will be found below index 5 because index 5 value is 42. If 25 exists in this, array, it has to be between 0 and 5 because everything above 5 is a number greater than 42, greater than or equal to 42 actually, right? So if my 25 exists in this array, it has to be on the left of this index 5, right? So what I'll do now is I will change my R to 5. So left and right basically tell me which part of the array can this element lie if it exists, right? That's what it means exactly. This is the left of the sub array that I'm interested in. This is the right of the sub array that I'm interested in. So now, since my 42 is greater than 25, I will move my R to 5. I'll move my R to 5. Now I will do, okay, my L now is 0, my R now is 5. Now what is my middle element now? 0 plus 5 by 2, and when I round it up, I get 3. Right? I'm rounding it up, right? So now I'll check the third element. The third element is 32, right? When the third element is 32, I will compare 25 with 32. Again, 32 is still greater than 25, which means that my query point, if 25 exists in this array, it has to be less than the third index. It has to be somewhere in this array now. It has to be somewhere in this array. So I'll make my R equals to 3. I'll make my R equals to M now. Now what happens? My L equals to 0. my R equals to 3. Now what will my M look like? My M will be 2. 0 plus 3 by 2, right? 0 plus 3 by 2, when I round it, I'll get 2. Now I'll go to the second element. Because my L is 0, my R is 2. 28 is still greater than 25. Right? So what is the subarray that I'm left with? I'm left with 0, 1, 2. This is my L, this is my R. And I have 23, 25 and 28. Right? I know that in this subarray 25 should lie. Right? Now what I'm doing, now I'll break this further. What is the central element here? Right? It's 2. So I'll keep breaking it up till the time I find my 25. If the number doesn't exist, you'll just reach a stage where L equals to R equals to M, because all of them will point to just one number. That's called the termination case. Now the fun part is this: how do you analyze this algorithm? So let's look at it geometrically, right? So I have index 0, index 1, index 2, so on, index n minus 1, index n minus 2. So at the first iteration, first time when I'm comparing, I'm breaking this array into 2 parts, and I decide whether it's in this part or in this part. With the first comparison, if my array at the start of the first comparison, my array is of size n, right? Because my element could lie anywhere in this amongst these n elements. But after the first comparison, I decide that either it lies in this left subarray or right subarray, right? So what is the number of elements that I have at the end of my first iteration? I have n by 2 elements. After the first comparison, I have a space of only n by 2 elements that I need to be compatible, because I'm breaking exactly into half, right? Now, after my second comparison, what happens? After my second comparison, let me change the color here. Okay, let's assume I decide that it's here. I break this again into 2 parts, equal parts, right? So now what is the size of this subarray? This subarray will be n by 4 size, right? After third comparison, it will be n by 8, right? So after first comparison, it is n by 2. After second comparison, it is n by 4. After third comparison, it is n by 8. After fourth comparison, it is n by 16, so on and so forth. At some point, this will reach one value only, because the size of the array is decreasing. At what value will this be? So let's say n equals to 16. Okay, then at 4, this value will become 1. If n equals to 8, at 3, this value becomes 1. If n equals to, let's say, 32, at 5, it becomes 1. So 5, 32, 4, 16, 3, 8. Now you see the logarithmic relationship here. What is log of 16 base 2? It is 4. What is log of 32 base 2? It is 5. What is log of 8 base 2? It is 3. So at log n base 2 comparisons, you have reached exactly one element, which means what is the total number of comparisons that you have to do? In the worst case, you will do log n comparisons, which means this algorithm takes order of log n time or comparisons, right? Very, very simple. So binary search basically breaks your array into subarrays of size half. And all of this, remember, all of this will work if and only if your list is sorted. Otherwise, this whole thing breaks down. Okay, this is a very, very simplified explanation of binary search. Now let's look at some simple code to see how that works. Okay, here we use recursion. We learned about recursion, right? So I have my left and right given any array, and if x is the element that I want to find, first I check if r is greater than or equal to L, right? Because that's what we said, right? L is here, r is here. If r is not greater than or equal to L, then you say, okay, I've reached an end state, I'll get out of this loop, right? This is called the base case. It's called the base case of recursion. We learned about the base case or the limiting case of the boundary case of recursion, right? Here I'm computing the midpoint. I'm checking if the midpoint equals to this, or if it is greater than, or if it is less than. If the midpoint is, so here the algorithm runs like this. I have my L here, I have my R here, this is my midpoint. If my midpoint is greater than X, or my query point, here X is nothing but your Q, right? Then I'm saying binary search, if it's greater than, if my midpoint is greater, then my data should lie here. What am I doing here? I'm saying my L will remain L, my middle point, my right point becomes middle point minus 1. Right? And I'm doing, and again calling binary search within the binary search function. That's called recursion, right? Very simple. I ask you to try this. I ask you to run through this. The recursive algorithm, right? Because in the binary search function, we are calling binary search again. Because that's how this algorithm neatly fits in, right? You have a bigger array, and then you say if this array, if this element is greater than or less than, you either search in this sub array or you search in the sub array. And you recursively break this array into pieces, right? Logically. So those of you who have studied binary search, this will come very, very simple to you. And I recommend you go through this function. And this function has been taken from Geeks for Geeks with some small modifications. But Geeks for Geeks is a great place if you want to learn and practice algorithms and data structures. Okay. So I just wanted to, so this is the order of log n algorithm given a sorted array. Otherwise, say, look at it. At the start, I'm taking my array, my list L, and I'm sorting it. Otherwise, this algorithm does not work.